Hello everyone, welcome to the next lesson of numerical integration. In this lesson we are going to learn about various methods that are being used to calculate the integration of a function or equation. Okay. So we have already learned about Newton-Cotes formulas or the closed methods, which are trapezoidal rule, Simpson's 1/3 rule or Simpson's 3/8 rule. So those rules can be easily applied to both tabulated data and functions or equations as well. But there is a problem whenever you are using those formulas for calculating the integration of a function or integration, because those methods cannot actually reap the benefits of having a function or equation. Those closed methods, Newton-Cotes formulas, were especially used for tabulated data, but for functions or equations we have more fundamental methods and more approximate methods that are going to be discussed in this lesson. Okay, let's say we have a function. Okay, we can easily calculate the integration over a limit for this function. So if you just go to the details, so let's say we are showing you the details of the integration results. So if you just apply the trapezoidal rule, we have a specified lower limit. We cannot go for a higher accuracy beyond this limit. So this limit of trapezoidal rule has a limit of precision which is of the order of 10 to the power minus 4. But if you use the Simpson's rule, that will have a limit of precision which is of the order of 10 to the power minus 6. Okay, so if you want more precise results, you cannot have using these methods, trapezoidal or Simpson's rules, because those have a specified limitations. Okay, so that's why we need further methods that can actually use the benefit of having a function or equation. So these methods include Romberg integration or adaptive quadrature integration or the Gauss quadrature integration. So these are the three common methods that are being used to find out the integration of a function or equation. So let's see some of the basic ideas of these three methods. The first integration method was the Romberg integration. It's based on the Richardson extrapolation. Richardson extrapolation is a method that combines the two numerical integral estimates to obtain a third result. That means if I have already achieved two results with two different values, I can have a more accurate value by using these two preliminary results. So that's the basic idea of Richardson extrapolation. The next method was adaptive quadrature integration. This method dynamically changes the width of each of the segments. Let's say we have a function that in some segments this function has a behavior which is very much constant. That means the function is widely the function that has a change which is the function is changing very much slowly. So in those segments we can apply a smaller segment, we can apply a segments which have a larger width, but in those areas where the function has larger peaks, in those areas we have to use a smaller segmented portions, and that's the definition of adaptive quadrature integration. It dynamically changes the step size or the width of the segments. Okay, so it has a special benefit. So whenever you are visualizing the effect of these approach from the computational perspective, you can have a desired global accuracy with least computational effort. So that's the benefit of this method. Okay, so the last method was Gauss quadrature method. It employs the x values, that means the independent variables that are positioned between a specific locations inside that boundary. So among these three methods, we are just going to discuss the Romberg integration method in details, and we will just show you some of the links that will be helpful for you to find out these extra methods like adaptive quadrature or Gauss quadrature methods. So we are just going to find out the basics of Romberg integration. Romberg integration is one technique that is designed to attain efficient numerical integrals of functions. Okay, so we have already said that we cannot just use the actually we can just for the analysis purpose the trapezoidal rules or the Simpson's rules, but we cannot have the desired accuracy with those methods, and that's why we need to go for extra methods like Romberg integration or other methods. So Romberg integration is based on the ideas of those preliminary methods, like we can still apply the trapezoidal rules or Simpson's rules, and with those results we can get a further better result using Romberg integration. So that's the basic idea. Romberg integration is not a new algorithm, rather it employs the algorithms of trapezoidal or Simpson's rule, and with those results it approximates a better numerical value. So that's why we are going to learn about the Romberg integration and the Richardson extrapolation. Let's first see what Richardson extrapolation is. Let's say we have already two estimates of an integral, so that we can use those two methods, those two results, to compute a third result which is more accurate and more precise. Okay, so the estimate and the error associated with a multiple application trapezoidal rule can be represented something like this, which is I equal to I of h plus E of h. Here I is the exact value of the integral. Okay, this is the exact value of the integral. I of h, the approximation form an n segment application. So this formula that you are watching here, this is the general formula for a normal multiple application of trapezoidal rule. So what the same rule that you just learned in the previous few slides. So this formula denotes the final result that was achieved from the trapezoidal rule. So I is the exact value and I of h the approximate value that we have achieved using trapezoidal rule. So and E of h, this is the error. H is the step size. Step size is denoted as the upper limit minus the lower limit divided by the number of segments. So n is the number of segments, and here E of h the truncation error, the normal error. So that's how we can just specify the exact value, the approximated result plus the error. That's how if we just sum over these two quantities, we will get the exact value. Okay, so that's the definition of true exact value of integration. So where does the Richardson extrapolation comes into account? Let's say I have two estimates of the true exact value using two different step size, h1 and h2. Using h1, I have the exact value which can be denoted as I of h1 plus E of h1. Similarly, using h2, I got the same exact value using the same formula, so I can express I of h2 plus E of h2. Since both of these methods, both of these approaches provide you the same exact value, that's why these two quantities are equal. Okay, so this is equation 1. So for a multiple application of the trapezoidal rule that we have already learned in the couple of few slides before, we can easily denote the error term E, which is a truncation error, something like which is proportional to the square of the step size. So this is an empirical formula which can be easily used to this equation 1. So E is proportional to the square of the step size or the segment width. So we can easily say E of h1 divided by E of h2 equal to E h1 square divided by h2 square. So this formula can be easily substituted into equation 1. So if we substitute equation 2 into equation 1, we will get this formula. So this is the result. So here we have E of h2 in both sides. So if we solve for E of h2, we will get something like this. So this is the approximated result of E of h2. So now if you just substitute the E of h2 into the exact formula, that means I of h equal to I of h2 plus E of h2. This was the method that we applied for if you just use the trapezoidal rule with a step size of h2. If you do this, if you substitute E of h2 into this equation, you will get a result something like this. So this is the final result. This is the Richardson extrapolation. So you have in this equation, you see on the right hand side, you have integral results with step size of h2 and h1. So using both of those results, you are just getting a better approximation I. So I is a result that has been obtained using previous results. So that's Richardson extrapolation. We are just using the already obtained results to calculate a more accurate result. So this has an accuracy, an error of estimation which is of the order of 4. Okay, I of h1 and I of h2, those had the order of accuracy or error of the order of 2, but we have now the order of accuracy to be 4. So that's a more precise result. So a special case, let's say we have h2 equal to h1 by 2. That means in the second case we are just making half of the, taking the width of the segment as a half of the first width of the segment. So h2 equal to h1 by 2. So if you just substitute these results into the main Richardson extrapolation result, you will get an a formula which is I equal to 4 by 3 I of h2 minus 1 by 3 I of h1. So this is the special formula that is specially derived for h2 equal to h1 by 2. So this formula is actually has an order of accuracy of 4. So with the results I of h2 and I of h1 both have order of accuracy to be 2. So order of accuracy to be 4, which is more which has a finer accuracy. Okay, so you can, if you just extrapolate the idea of this Richardson extrapolation for further accuracy, let's say I got the result of order of accuracy with 4. I have two such quantities, so I can just use those two quantities again with Richardson extrapolation equation to get an order of accuracy of 6. Okay, in that case the formula should look like this. Similarly, if I have two quantities something like this with different orders, with different step sizes, and I have with both of those methods have similar order of accuracy to be 6, and if I just combine those results with the Richardson extrapolation, I will similarly get a far more better approximation which has an order of accuracy to be 8. Okay, so what I am doing here with just successively substituting the results from the previous step, I can get a far more better result. Okay, that's Richardson extrapolation. So this formula is specially designed for order of accuracy 8, and this is for order of accuracy 6. Okay, so let's look at an example. I think if you look at an example, that would be more clear to you about the procedure of Richardson extrapolation. So let's say I have a function here, f of x equal to, this is the function, and we have the lower and upper limits to be 0 and 0.8. So if you just apply the trapezoidal rule with this in this function, so you will get a specific accuracy and you will have a specified error limit, so beyond which you cannot go further. So that's why we are going to use those results using Richardson extrapolation. So let's say using trapezoidal rule and with one segment, two segment, or four segment, we got these integral results. Okay, so we are not showing you the total calculations here, so you can just go for the examples that I have shown you in the trapezoidal example lesson. So you can just use those lessons to calculate the integral variable using these separate segments. Okay, for each of these segments, let's say I have one segment, then the value of h should be 0.8. if I have two segments, then value of h should be 0.4. that means 0.8 minus 0 divided by 2. Similarly, if I have 4 segments, I will have a h to be 0.2. So for each of these segments and step sizes, I will have the integral variable to be something like this. So these are the results of this integration, and for each of those cases I have the errors specified. Okay, so these are the preliminary results. So now I am going to use the Richardson extrapolation so that I can use these preliminary results to calculate for a further more accurate result. Okay, so the true result is already given in the question, which is 1.640533. so this is the true result. Let's see how we can use the Richardson extrapolation. So this is the table, this is the preliminary results. So for the first two results of 1 and 2 segments, that means I of h1 is 0.8 and h2 is 0.4, and the I of h1 is 0.1728, I of h2 is 1.0688. So if you just use these formula, use these values to calculate a further more accurate results of the order of accuracy to be 4, then use these Richardson extrapolation. Why we are using this? Because these results, the preliminary results, are of the order of 2, order of accuracy which is 2, but now I am going to calculate the order of accuracy of 4. Then the formula I am going to use is something like this. Okay, so if you just substitute these results, I of h2 and I of h1, and which is the result is something like this, 1.367467. Also see that h2 is h1 divided by 2. As a result, we are just using the spatial formula that I have derived. So if this was not, then you just use the original Richardson extrapolation equation. So you can just do that. So the result with the first two results with the order of accuracy is 1.367467. So if you just calculate the error, it is 16.6%. Okay, so to look at this table, with segments 1 I have error 89%, with segments 2 I have error almost 35%. But if you just use these two results with Richardson extrapolation, you will get a result which has an error of 16.6%, which is very low compared to these two ones. Okay, similarly I can use these other two results, like means segments 2 and segment 4. If you just use Richardson extrapolation, you can get the result, and the result would be something like this. The same formula we are going to use, because h2 equal to h1 by 2 in this case also. So as a result, the result will be 1.623467. so this is the result. This is the numerical result with these two segments. So in this case, the approximated result with Richardson extrapolation has an error of only 1%. But here in the original cases, the error were 35% and almost 10%. But now I have an error of only 1%. So this is lower than both of those errors. Okay. So that means Richardson extrapolation is providing you a better approximated result for the integral value. So you can use these two preliminary results. That means with the order of 4, accuracy of 4, you can use these two better results to obtain a further better result with Richardson extrapolation to have an accuracy of the order of 6. So if you just use this formula, as I have already shown you a couple of slides before, using the better results, you can have a further more better accuracy with 1.640533. Okay, so this is the result which compared to the original result, this result matches the true result up to 7 significant figures. Okay, so this is very accurate. So you just started with the preliminary results of trapezoidal methods, and with Richardson extrapolation you have just got a far better result, which is very important actually. So in this lesson we have learned about the Newton course formulas limitations. There are some limitations of those Newton course formulas, like trapezoidal rules or Simpson's rules, and we have shown you that the Richardson extrapolation can provide you the better result based on those preliminary results of Newton course formulas. So Romberg integration, we have seen that this Richardson extrapolation is a basic of Romberg integration. Although we have not gone for the Romberg integration till now, we will go for that method in the next lesson, but we have seen the Richardson extrapolation. So in the next lesson we are going to see how this Richardson extrapolation can help you to using the Romberg integration method. So this is the discussion topic in the next lesson. So till then, thank you so much.